To tell, we have today only one speaker for this webinar series today, because José Vicente Ros won't be available to participate. And fortunately, we will be able to reschedule his webinar, hopefully next month, but we will let you know about that. So now this is my pleasure to introduce the speaker of the day, who is Dr. Dana Pisk. Dana is an assistant professor at the Department of Chemistry at the University of Zagreb since 2018. Prior to her appointment at the University of Zagreb, Dana obtained the prestigious Marie Curie postdoctoral fellowship for developing research in catalysis for oxidation reactions. And today she will tell us about the application of porous and non-porous materials based on transition metals in oxidation reactions. So Dana, please, the slot is yours.
Thank you very much, and thank you for this nice introduction. I will share a screen so you will say me if it is possible that, if it works, it's okay?
Yes.
Okay, and if I put it on the large screen, if I go through the presentation, you can see how it goes or not? No?
No.
Nothing.
Not yet.
But you can see the first slide or you can't?
Yes, we can.
Now it works?
No.
And can you see it like this?
We can see your first slide and yeah, but it's not full screen. Yeah.
Yes,
it's fine.
The second, but on the full screen, it doesn't work.
Okay, you can go on. We can see the second. We can see the second, so it's okay.
Yeah. Okay, but on the full screen, you can't see it.
No.
Okay, so we will do without the full screen if it cannot go. I apologize for that. So as you heard, the headline of this today's presentation, today's webinar, is application of porous and non-porous materials based on transition metal oxides in oxidation reactions. And in fact, what I will present you today is not only the part of the research that is the part of the Netpore, that was the part of this project proposed to the I mean, as a part of the Netpore section, but it's also a little bit about the catalysis, because the catalytic application was not the point that was existing in this kind of research that was presented by Netpore action. So first thing is I will speak a little bit about my scientific expertise and what I usually do in my career. And in fact, the first part of my research was oriented towards the preparation of the complexes. And in fact, it is the key point of this preparation of the complexes were the coordination complexes of transition metals. Transition metals that were usually incorporated in this kind of complexes were molybdenum or vanadium transition metals. And when I got the coordination complex, there were a lot of methods that were used for its identification. For example, infrared spectroscopy, NMR spectroscopy, then the TGA or the diffraction methods, depending if there was a single crystal or if there was a powder sample. And in the end, we started to apply the obtained complexes, the obtained materials, and we tested them as a catalyst. And in fact, the first part of this kind of reactions and of the catalytic application started now very far ago, I mean, a long time ago. In fact, it was 2011, and it was the first time that I spent in France, and I started to work with Professor Agustin there and Professor Poli. And in fact, we tested the samples in the oxidation reaction. And the reactions that we tested were the oxidation reactions, the epoxidation of cyclooctene. The desired product that we wanted to obtain was the epoxide, and we tried to perform the reactions under the conditions of green chemistry, meaning that the oxidant that we started to use was the TBHP, so terzbutyl hydroperoxide, that was available in a water solution. Another thing that we tried to diminish was that we didn't add any kind of organic solvents to this reaction mixture. And usually it is known that organic solvents would would help the reaction to get the better catalytic results in terms of, for example, activation of the catalyst and the selectivity towards the desired product. The results that we got here were quite successful ones. And as you can see, the results that we do see here. Yes, could you please mute it? Okay, there was the reactions that were present. In fact, were the reactions where we worked on minimal catalyst loading. And when I say minimal, you can see the ratio of the complex and the olefin that we used. And the first results that we obtained were quite impressive because this kind of complexes, we got a very good catalytic conversion. So the epoxide, so the cycloctene conversion was quite high, and the selectivity towards the epoxide that was desired product was also very well. We did more detailed research, and we tried to successfully publish those results, which I will not speak in the details. And with the years, we moved to different kind of complexes. And in fact, those were the complexes that were not only the simple coordination complexes with transition metals, but we moved to the area of polyoxometalates. And in fact, the polyoxometalates that are presented here are having the general formula where the polyoxometalate ion was the Lindquist type of ion. So it means that it was MO6O19 species. And in fact, the cationic part of the complex was the molybdenum coordination complex. There were two types of molybdenum coordination complexes that were used as a cation of these materials. And one of those complexes was this chain-like complex, zigzag chain, which was one of the first reported examples of this kind of complexes. And the second complex you can see on the right, in fact, it was the dinuclear complex that served as the cationic part. We also tested these kind of complexes under green protocols. So it means, again, we didn't want to add the organic solvent to the reaction mixture. And we used the cycloctene as a substrate and TBHP in a water as oxidant. As the research was continuing, we got again quite good results, and we suppose that catalytic activity of this kind of complexes, there are two active sites of this kind of complexes, and one active site comes from the Lindquist type of an ion, and the other catalytic site comes from simple molybdenum coordination complex. We understood that by those kind of reactions, the reactions that we presented were in the area of homogeneous catalytic processes. So it means that the catalysts that were used were in fact molecular catalysts. And during the reaction, some of them were more soluble, some of them were less soluble. And in order to get the catalyst that could be recycled and reused, we started to think about the heterogeneous catalysis. And when we thought about the protocols that we can apply, we wanted to stay in the area of green chemistry. So it means that we wanted to use the oxidants that were less harmful and more ecologically appropriate. And for that reason, we decided to use the hydrogen peroxide because it's quite cheap oxidant. And the only byproduct during the reaction could be water, which in fact could be quite easily purified at the end of the reaction. We moved to the area of heterogeneous catalysis, and it was the main point of my postdoctoral research, we started to prepare the simple molecular catalysts that are shown on the upper part of this slide. And in fact, they were commercially available. It was very simple reaction, and by which we use the commercially available polyoxometallate acids. And in fact, we did the complexes with something called ionic liquid. And the idea was to fix those catalysts on some kind of support. For this kind of support, we decided to use the Merrifield resin chemistry because they're used for the synthesis of peptides, and we gave them another role because we use them as a support for our catalysts. The reaction that we were in fact interested and that we presented as a positive result of this product was the preparation of adipic acid. And in fact, adipic acid is one of the main intermediate products for the preparation of nylon. And in fact, 86% of nylon, of adipic acid is used for the preparation of nylon. In fact, as you can see, large companies are producing the nylon, and in fact, they need adipic acid. And that is the point of the research, because we got the product that could be highly incorporated and used in the industry. The research presented it in this kind of this part of my career was also published, and we continued further and we moved towards some kind of supramolecular structures. And the question is now, why those supramolecular structures? I mean, there is a possibility first to design the structures, to design the motif that we want to get. And of course, the synthesis of this kind of complexes is not the most simple one, but it is possible to achieve the complexes that are having the supramolecular motifs. And in fact, they're having this kind of holes. Here are presented 3 different tetranuclear molybdenum complexes, and 2 upper complexes show more or less similar structure, similar geometry, while the complex down has some kind of different structure. In fact, it is a zigzag complex, and we tested those complexes for in the reactions of cyclooctene epoxidation and cyclohexene epoxidation. When we tested the complexes for the cyclooctene epoxidation, we tested them by using TBHP in water in order to follow the green protocol. And those are the results that are presented here with the full dots. With the full dots. The dots that are white, so the blank dots. And also we tested the TBHP indicane as the oxidant, and those are the results that are presented in full colored dots. As you can see on those slides, we found 3 different very good catalysts that are quite active after short time of the reaction. And the catalyst that is presented here with the green lines is active, highly active, I mean very highly active, only after 20 minutes of the reaction. The other 2 catalysts are also active, but they need some time to get activated, and it's called induction time. All other catalysts that we're using as oxidant TBHP in water show less activity, but when comparing it with other literature results, it's quite good also. Excuse me, I do not hear well. Somebody was saying something? Maybe not. Okay. The other thing that was more oriented towards the headline of the presentation that you saw, it is the research that we started to do in 2022. And in fact, it concerns the application of new method, impedance spectroscopy, that is usually used for the testing of electric and dielectric properties of the compounds of the new class of materials. And in fact, what we saw as being part of a group of this cost action, we proposed some kind of research in this regard. First thing that was positive and that was in fact used as a background for the presented research is that the impedance spectroscopy, there are some literature examples that the impedance and for the investigation of electric properties of transition metal complexes with the Schiff basis, and that those kind of researches have potential. We try to use the impedance spectroscopy also as the method to research electric properties of simple complexes. Here is the case of molybdenum complexes. It is deoxomolybdenum complexes. They have the tridentate ligand that is coordinated to the metal center. And usually what we do, we do the thermal analysis of this kind of complexes. Why to do the thermal analysis? Because we want to get the insight in what is happening with the sample, with the material, by the time that it is heated. In fact, what we can observe from thermogram, it is that if we have the compound that has solvent in its structure, then we can see the solvent release, and after we can see the degradation of the complex. We try to do we try to test the electric properties of this kind of compounds, and we applied impedance spectroscopy. And in fact, what we also observed that the impedance spectroscopy is a very good method that can be correlated, and the results that we get by the impedance spectroscopy can be correlated to the results that we get by the TGA, so thermogravimetric analysis. What does it mean? That also by the impedance spectroscopy, we can see the difference if we have the sample that has the solvent that is incorporated in its structure, and by the time that the solvent goes out, which what we can follow in the TGA curve, we can also follow by the results that we get from the application of impedance spectroscopy. We get the different conductivity of the samples, and in fact, it was the basis for the small project that we presented in this kind of is the research that is based on the new type of materials. In fact, the case here is the type of materials that are considered as glasses or glass ceramics. And those are materials that contain a high amount of vanadium in its content. And in fact, also they contain some kind of alkali metal, and they can contain different transition metal that is added to structure. And what we supposed, we wanted to test that how will the vanadium content, how will another transition metal content, and how will alkali metal content influence on the catalytic activity of those complexes. In fact, just by the literature research, there are not so many glass and glass ceramic systems that have been tested in catalytic applications. Usually glasses and glass ceramics are tested in electrical for their dielectrical or electrical properties, and they're known to be they can be used for the different battery production, battery setup, for example, but the catalytic properties of those kinds of materials are quite poor. And here you can see some kind of results that we were able to find in the literature. And in fact, it was just the key point that the catalytic reactions could be tested. There are some positive examples, and what we thought by all the research and all the data and all the results that we have from the previous researches, we supposed that if we will have the glass with higher content of vanadium, that it could be quite okay catalyst. For that reason, several samples, set of samples were prepared, and they had a different vanadium content, different alkali metal content, and different other transition metal content. And for example, as alkali, the sodium ions have been used, and vanadium was used as the main transition metal oxide. In this glass and glass ceramics, there were also phosphorus atoms, so it means the phosphorus oxide was used as a starting material, and the transition metal, other transition metal that was added to this system was the niobium as a part of a niobium oxide. The first test that we did, we wanted to test the reactions of cyclooctene epoxidation by using the TBHP in decane and TBHP in water, and we wanted to compare those systems. Because on the previous results, we suppose that TBHP in decane should be the better oxidizing agent, and we didn't know, we didn't have any kind of experience with these kind of reactions. The first testing we did with the TBHP in decane, and in fact, the results, the catalytic profiles are presented here, and three best systems, three best materials for this kind of reactions contained high loading of vanadium. And also, we can see that the samples with sodium and niobium are more or less the same activity at the end of the reaction, meaning after 6 hours of the reaction. When we diminished the amount of vanadium to 55%, in fact, then we got also the active compound, but less active than with 70% of vanadium. Then we try to compare the oxidants, and in fact, we use TBHP in water and TBHP. Sorry, here are the results with TBHP in decane. And in fact, we try to diminish the quantity of the catalyst. And we diminish the quantity of the catalyst to half, because we wanted to see if the catalyst loading, so it means if we diminish the catalyst loading, what will happen with the activity. And we can see here that the activity with large amount of catalyst or less catalyst is not so significantly different, meaning that we can continue the research with fewer catalyst, so with a quantity that is not so high. And again, we got quite good results with both amounts of catalyst, both catalyst loadings. At the end, we compared the influence of oxidant, and in fact, we used TBHP in decane and TBHP in water. And also here are the results presented with the colored dots and the empty dots. And it can be seen that there is not such a significant difference by the use of oxidant, meaning that green oxidant, so it means TBHP in water, is quite good oxidant because it means that the green protocol during this reaction can be used. Also, what we did compare the selectivity parameters. Selectivity towards cyclooctene epoxide was compared. And here are the results presented for the TBHP in decane and TBHP in water. So the oxidant was either TBHP in decane or TBHP in water. And all the samples with the stars are, in fact, the samples that were participating in the reaction with TBHP in decane. Also, what we can see that the selectivity for the sample that contains higher content of vanadium is samples with less vanadium in its structure. And also what we can see, the selectivity with TBHP in decane or TBHP in the water is more or less the same. Which is quite good, again, and supporting the principle of green chemistry and what we can follow with the green chemistry. At the end, what we try to do with those samples of glasses and glass ceramics, and in fact, it is the fatty acid oxidation. And in fact, this is just the preliminary results for the oxidation of stearic acid. Usually, this reaction is followed it is not followed by the GC, but it is followed by the TGA analysis. And in fact, what we suppose by the time that we are using the catalyst, the temperature of degradation of stearic acid should be moved by the lower value, meaning that in fact the catalyst has its role. These are still the results that should be more researched and will be more researched and will be optimized. And in fact, we are planning to follow this kind of results with a TG infrared system that is working together. And we believe that we will be able to quantify the products that we are getting from all those results. At the end, there are a lot of things and a lot of questions that arise from this kind of research. So this is the first research of glass and glass ceramics in this kind of epoxidation reactions that are followed either by oxidant in organic solvent or oxidant in water. And in fact, there are a lot of questions to be answered. For example, which kind of catalysis this is? Are those catalysts homogeneous or the molecular ones? Or they are the heterogeneous ones. What we saw that some of the catalysts are soluble during the reaction process. So this is definitely the question that arises. Then also the question that could follow the complete research is, what is the role of vanadium? Is vanadium role the crucial one for the activity, or there is also the contribution of sodium ions and niobium metal oxide that is added to this mixture? Of course, we should work on the recovery and recycling results, because if we have the catalyst that we can reuse, it is the benefit of the complete catalytic procedure. And some of the preliminary recovery testings have been done, and in fact we got a very positive results, and the activity remains maintained, which is very important for this kind of materials. And of course, the last question that arises from this, that the porous materials that are usually tested in different kinds of applications, I mean, this type of glasses and glass ceramics can be also tested for the catalytic reactions that they were not tested before. And we believe that there is certainly application in this regard. With this, I would like to close this talk and close this research. The last part of this this presentation was part of the project that I got the fellowship as a part of Netpore Action, and I'm open for all the questions that you would have.
Thank you. Thanks a lot, Jana. We have time for a few questions. Do you have any? You can raise your hand from the Zoom, excuse me, or start talking directly if you have any question to Dana. Okay. I will start with a couple of quick questions, Dana. Thanks a lot. It's really interesting to see how you can use porous material in this great expertise of catalysis for epoxidation and others oxidation reaction. You are expert in. My question comes on the porous material part. Since you're using glass or glass ceramics, what would be the ideal porous material for you in this heterogeneous process of catalysis here? In terms of texture, price, I guess, or?
Well, I mean, the very good point and advantage of those materials, they are prepared for the chemicals that are quite cheap, which is, I think, the great advantage of the complete process. Because those glasses and glass ceramics are prepared just by the spontaneous processes. So it means that the mixture of the oxide was heated on a certain temperature, and then it was just cooled down. And this cooling was not, in fact, at the beginning, the samples that we used here, the cooling process was not determined, like we could not control it. It was non-controlled cooling of the melting of the mixture that we got by melting. And in fact, some of the materials that we have show the crystallinity, and some of the samples are amorphous, in fact. And it would be good that we can control the crystallization process. So it means that we can control when we can get the glass ceramics. And in fact, it will be the point of the next research. And also what would be good, it would be good to control the solubility of those materials. And we believe there are some researches that the solubility of those materials could be controlled by the ratio of vanadium oxide and the phosphorus oxide. And in fact, the higher content of phosphorus oxide should help the system not to be soluble. And maybe it is the way to work on the heterogeneous catalyst. But I think it will, again, open the new area of the research because it is so complex that we thought we wanted just to test if those materials can be tested for the reactions that we have the experience in. And now it opens a lot of questions that are arising from it. So I think it is definitely the benefit of it.
Great, thank you. And would it be interesting also to control the textural properties, the porous volume, porosity?
For sure, yes.
Control of this?
Yes, because
ceramics.
Excuse me, could you please repeat?
Do you have any control already of the surface area, porous volume?
It is also another research. Usually it should be, I mean, for the catalysis, the surface is quite important, and it is proven that if the surface is large, the catalytic reaction should be, I mean, the catalytic material has more potential and should be catalytically more active. And in fact, the different ratios of those oxides are something that gives the possibility to control the grains, in fact, that are forming those materials. And in fact, here, some particles also have the possibility to form nanoparticles, and definitely this size of the grains that are in the material is something that is important to control and to achieve in the further research.
Great. And in terms of upscaling, you're fine with this approach, right? Or it has
yes.
Yeah.
Yes.
That's very interesting. Thank you.
You're welcome.
Any other question? Oh, yes. Bunel, please. I have a hand raised here. Yeah.
Yes. Thank you for a nice and informative presentation. And I have one question. Is it possible to oxidize functional groups located on the surface of graphene oxide monolayer through your oxidizing phase?
I'm very sorry. I'm very sorry. I cannot understand. If somebody can write it or something, please.
Okay.
Have interferences. We don't hear you very well.
There is a lot of noise. I'm sorry.
Yeah. I'm sorry. Okay.
Could you type the question? Okay. Just open it. Yeah. Is it possible to oxidize functional groups located on the surface of the graphene oxide nanolayers through your oxidizing agents? As you know, there are various functional groups on the surface of the graphene oxide. Aldehyde, hydroxyl, epoxyl, blah, blah, blah. For the functional groups of the surface of graphene oxide must be carbonyl group, and we chlorinate it through thionyl chloride. These are not the graphene materials. It is, in fact, the mixture of vanadium oxide and phosphorus oxide. So it means that there are vanadium of oxygen phosphorus bonds, and by incorporation of niobium, there would be the bridges, so the bonds vanadium, oxygen, niobium. It is, I mean, the functional groups are different. In fact, about this part of the chemistry, I'm not the expert in that. So there is certainly a way maybe to functionalize those materials, but I do not have the experience in that.
Oh, thank you. Thank you.
You're welcome.
We can have a couple of additional questions, if there are any, for Dana today. Nope. So if not, then let's thank Dana again for this great talk, and thank you all for your participation to this webinar, and we hope to see you in a month thank you very much, Dana. That's great.
Thank you also.
Thanks a lot for your talk. And,
Thank you.
and all have a great day. Bye-bye. Oh, maybe one question? Wait, no?
No,
No,
it was
no.
a mistake.
Yeah, yeah, I think so. Okay, so have a great day and see you in a month. Thanks a lot, Dana, for your great talk. Bye.
Bye. Thank you.
Merci beaucoup. Alors désolé, on n'a pas mis le son parce que là je suis en direct d'un TP moi. Donc
Ah.
voilà. Et donc pour info, là vous avez